Welcome to our universe. Right now, while you lie still, the universe is quietly withdrawing, not violently, just steadily, the way a tide recedes in the dark. Galaxies that were once within the reach of physics drift past a threshold beyond which no signal, no light, no information can ever return. The threshold is not a wall. It has no surface. It is a consequence of the speed of light and the age of time. And beyond it lies a cosmos we have never seen, cannot reach, and may never fully understand. We'll spend tonight in that direction, looking past the edge of what we can receive, into the part of the universe that has been there all along, doing its quiet work, completely without us. If this feels like your kind of place, subscribe. Every person who finds their way here makes this universe a little more ours. Because this universe has always been larger than what we can see. Let's begin. The horizon is not a wall. The word edge has never quite applied to the observable universe, though we keep reaching for it. When scientists talk about the cosmological horizon, the edge of what we can observe, they don't mean a physical boundary. There is no surface out there, no membrane, no point at which the cosmos becomes something different or something less. The horizon is a consequence of physics, not a feature of geography. It's the limit of what we can receive. Everything beyond it exists. It simply hasn't had time to send us a signal yet. The observable universe is roughly 93 billion light-years across, a sphere, with us at the center, not because we are special, but because we are the observers. Any observer, anywhere in the universe, would be at the center of their own observable universe. Each horizon is local, each one is personal, and beyond each one, the cosmos continues. The total universe, what exists beyond every local horizon, is almost certainly much larger than what we can observe. How much larger? Here the numbers stop being useful. Current constraints suggest the total universe is at least 250 times wider than our observable patch, and some inflationary models predict a universe so vast that the observable portion is genuinely negligible. A single bubble in an ocean whose size cannot be estimated from inside it. That ocean is what we're exploring tonight. Why does the horizon exist at all? The universe is approximately 13.8 billion years old. Light travels at a finite speed. That means only light that has had 13.8 billion years to travel can possibly reach us. The most distant sources we can observe are near the edge of what's physically reachable, given those constraints. But the objects we see at the edge of our observation aren't 13.8 billion light-years away. They're more than 45 billion light-years away. The reason is expansion. While the light was traveling toward us, space itself was stretching. The source moved, carried by the expansion, even as its light traveled toward us through that expanding space. So the observable universe is 93 billion light-years across, even though it's only 13.8 billion years old. Light traveled at most 13.8 billion light-years in that time. But space moved the destinations. This is the geometry of our situation. We sit inside a sphere of received light, surrounded by a cosmos that has been expanding for the entire history of time, carrying most of itself beyond any reach we will ever have. The horizon is the edge of our sight. It is not the edge of existence. And right now, as your chest rises and falls, photons are passing through your body that have been traveling since before the solar system formed. Ancient light that will pass through the atmosphere and out the other side, continuing into a universe that does not care where we are and will not stop when we sleep. The observable universe contains 2 trillion galaxies and represents almost nothing. In 2016, a team led by Christopher Consellis at the University of Nottingham published a revised count of galaxies in the observable universe. Using Hubble's deep field images, photographs taken by pointing the telescope at an apparently empty patch of sky for hundreds of hours, and combining those with theoretical models of galaxy formation, they arrived at a number: roughly 2 trillion galaxies within our observable patch. 2 trillion. The previous estimate had been around 200 billion. The revision came not from discovering the universe was fuller than expected, but from recognizing how many small, faint early galaxies have since merged into larger ones that current telescopes can detect. When you account for the galaxies missed by instrument limits, the count rises steeply. 2 trillion galaxies, each containing, on average, somewhere between 100 million and 1 trillion stars. Some of those stars have planets. Some of those planets sit in temperature ranges where liquid water is stable. Some have been around longer than Earth. But here is the part that matters. 2 trillion galaxies is the count within the observable universe. The observable universe is not the universe. If the total universe is 250 times wider than what we can observe, a conservative estimate from the flatness of the cosmic microwave background, then the number of galaxies in the total universe is not 2 trillion. It's on the order of 500 quadrillion, 5 followed by 17 zeros, and that's still assuming a finite universe. If the universe is infinite, the count is infinite. Every galaxy contains stars. Every star we know of formed from the same physics that formed ours. Beyond our horizon, in regions we cannot see, all of that continues, unwitnessed, unknown, but almost certainly there. The observable universe is the wrong name for what we can see. Start with the experience. Looking at the night sky, you see stars. You see somewhere dark enough, a faint band of light that is the disk of our galaxy seen edge on. If you have a telescope, you see faint smudges that are entire galaxies, billions of stars each, compressed by distance into a single blurry point. That feels like observation. It feels like seeing. But what you're actually doing is receiving light that left those objects years, thousands of years, millions of years, billions of years ago. You are not seeing those objects. You are receiving their past. The star you call the North Star sent its light roughly 430 years ago. Some galaxies visible to the naked eye sent their light 2.5 million years ago. Objects near the edge of our observable universe sent their light when the universe was less than 1 billion years old. Observable implies something is being observed. but the objects at the edge of our observation no longer exist in the form that sent us those photons. The galaxies have evolved. Stars within them have been born and died. The universe has aged billions of years since that light left. We are not observing those galaxies. We are receiving their echo. The observable universe is not a snapshot of the cosmos at this moment. It is a layered accumulation of light from different eras, nearby stars showing us the recent past, distant galaxies showing us the ancient past, and the cosmic microwave background showing us the moment the universe first became transparent, roughly 380,000 years after the Big Bang. It's more like a geological cross-section than a map. Each layer represents a different time. The deepest layers are the oldest, and below the deepest layer we can see, below the cosmic microwave background, there is more universe, more time, more history that we cannot reach with light. It is opaque to us, not because it doesn't exist, but because the universe was too hot and dense for light to travel freely back then. A better name than observable universe might be the lit universe, or the visible past, or simply what we have so far managed to receive. Inflation produced more universe than physics can describe. Begin not with the beginning, but with the sensation of acceleration. Imagine something, anything, accelerating. A car pressing you back into your seat, a ball thrown fast enough to blur. Now remove the object, remove the motion through space. What you're left with is the mathematical abstraction of acceleration, applied not to a thing moving through space, but to space itself expanding. In the first tiny fraction of a second after the Big Bang, in the period we call inflation, the universe expanded at a rate that makes every other scale of motion in cosmic history seem slow. It doubled in size, then doubled again, then again, dozens of times at minimum, in an interval so short that it cannot be expressed meaningfully in seconds, only in fractions so small that the denominator requires a string of zeros longer than this paragraph. By the time inflation ended, thought to have occurred about a trillionth of a trillionth of a trillionth of a second after the start, the universe had grown from something smaller than a proton to something roughly the size of a grapefruit. That sounds modest. The expansion factor was at least 10 to the 26th power, a number with 26 zeros. Some models put it far higher. What inflation did, beyond establishing the large-scale structure we observe, was distribute the universe across scales that dwarf what we can see. Before inflation, everything that would become the observable universe was contained in a region smaller than an atom. After inflation, that region had been stretched to the scales we observe today. But inflation didn't expand only what would become our observable patch. It expanded everything, including regions that, even after all these billions of years of subsequent expansion, are still too far away for their light to have reached us. Those regions are real. They have the same physical origin as our observable patch. They are filled with the same fundamental particles, the same forces, the same laws, because they inflated from the same initial conditions. But they are separated from us by distances that light cannot cross in the age of the universe. The observable universe in that light is something very small, looking at a very thin slice of an ocean it cannot fathom. Every galaxy beyond a certain distance is already gone forever. There is something genuinely difficult about the following. Every galaxy we observe beyond roughly 15 billion light-years away is already unreachable, not because of any failure of technology, not because of any limit that future generations might overcome, but permanently, physically, irreversibly. The expansion of space between us and those galaxies moves faster than the speed of light. No signal we could ever send, no spacecraft, no laser, no communication of any kind could cross that growing gulf, and no new signal from those galaxies can reach us anymore either. We can see them now because the light arriving now left long ago when the distance was smaller. But the galaxies themselves are already beyond the event horizon. What we're seeing is a delayed image of something that has slipped permanently from our reach. Those galaxies contain stars. Those stars contain planetary systems. Some of those planetary systems, by the statistics of probability, are not empty. Life, or something like life, may exist in those galaxies, but they are as permanently separated from us as if they existed in an entirely different universe. No amount of time, no advancement of technology, no discovery, nothing could close that gap. The expansion is accelerating. The gap is not staying fixed. It is growing. This is not a hypothetical future condition. It is the present state of things. Hundreds of billions of galaxies within our observable universe, visible to our telescopes, are already permanently beyond reach. The universe isn't just large. It is actively, irreversibly distributing itself beyond the reach of its own inhabitants. There is no good way to frame that, no image that softens it. It is simply true. The cosmic microwave background is the oldest wall in existence. What you think of as a photograph is not what astronomers mean when they describe a photograph of the early universe. Ordinary photographs capture reflected or emitted light from a scene as it exists at the moment the camera fires. The scene is there. The light bounces. The sensor records. Now, the cosmic microwave background is described as a picture of the early universe, the baby picture of the cosmos, as the phrase goes. But what it actually is something stranger. It is the light from the last moment the universe was opaque. For the first 380,000 years of its existence, the universe was so hot and dense that photons could not travel freely. They bounced constantly off electrons and protons, absorbed and re-emitted almost instantly, effectively trapped. The universe was a wall of plasma, thick and bright, preventing any signal from propagating across it. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, over a period of perhaps 100,000 years, which is sudden by cosmic standards, the fog cleared. Photons that had been trapped for 380,000 years were free to travel in straight lines for the first time. Those photons have been traveling ever since. They are the cosmic microwave background. We detect them today, not as visible light, but as faint microwave radiation coming uniformly from every direction in the sky. They have been stretched by the expansion of the universe from their original wavelengths into the microwave range. They arrive from all directions because the moment of release happened everywhere at once, and we happen to be positioned within it, not because Earth is special, but because any observer anywhere would see themselves surrounded by the ancient light from the moment of first transparency. What lies behind the CMB, earlier than 380,000 years, we cannot see with photons. The universe was opaque. We can probe it with other means: gravitational waves, neutrinos, mathematical models. But in terms of light, the CMB is the oldest wall. Beyond it is the unobservable early universe. The CMB is not just an image, it is the edge of light's memory. The recombination epoch was the loudest moment in history. When electrons and protons combined into neutral hydrogen atoms, the event that freed the cosmic microwave background, the universe was not quiet. It was ringing. For the 380,000 years before recombination, the universe was a plasma, and that plasma had been set in motion by tiny density fluctuations present at the very beginning. Those fluctuations created pressure waves, acoustic waves, that moved through the hot plasma at roughly half the speed of light. They compressed and rarefied the plasma. They propagated outward in concentric shells from every dense region. When recombination happened, those waves were frozen in place. The plasma cooled into neutral gas, and the acoustic vibrations were encoded into the density distribution of matter. Those frozen patterns are visible today in two places. The first is the CMB itself, tiny temperature variations across the sky, at the level of 1 part in 100,000, tracing the crests and troughs of those ancient sound waves. The second is the large-scale structure of galaxies, which shows a subtle preference for galaxies to be separated by a particular distance, about 500 million light-years. This is called the Baryon Acoustic Oscillation Scale, and it is a direct fossil of the sound waves that moved through the early universe. The original waves were real waves in a real medium, not metaphorical, not approximate. The early universe had a sound. It was produced by the physics of the Big Bang and propagated at speeds no human acoustic wave approaches. The amplitude was enormous. The medium was the entire cosmos. It lasted 380,000 years. Then it stopped, as suddenly as a bell held under water until the water freezes. We are surrounded right now by the fossil pattern of the oldest music in existence. Something pulls at scales we cannot see. The Great Attractor is a problem that cosmology has been sitting with for decades without fully resolving. In the late 1980s, a group of astronomers studying the motion of thousands of nearby galaxies noticed something unexpected. Galaxies in a wide swath of the sky were not moving the way they should, not following the expansion of the universe as cleanly as Hubble's law would predict. They were being pulled, consistently, measurably, toward a specific region in the southern sky behind the plane of our own galaxy, in the direction of the constellation Centaurus. the region was studied. It contains a massive concentration of matter, a supercluster complex called the Norma cluster and surrounding structures, amounting to a combined mass roughly 10,000 times that of the Milky Way. It was named the Great Attractor. But the problem persisted. Even accounting for the mass of the Great Attractor itself, the flow patterns of galaxies suggest something even more massive, even farther away. Something in the direction of the Shapley superconcentration, a massive region of galaxy clusters roughly 650 million light-years distant. That might account for more of the flow. But models still leave residual motions unexplained. Something may be pulling at scales we haven't fully mapped. Something beyond the Shapley, beyond the region our instruments have surveyed cleanly, in space that remains poorly characterized. We don't know what it is. And then there is this. Gravitational influence from beyond the horizon is technically permitted by physics. Gravity propagates at the speed of light, but the gravitational field of massive objects extends into their past light cone, which includes our region of space. Objects that were once within our causal past may have moved beyond our current horizon, but their gravitational influence, established when they were within range, is still present here. There may be things outside our sight that are pulling at us right now. That is not settled, not confirmed, but it has not been ruled out. Dark energy is erasing the universe, one galaxy at a time. Dark energy was not predicted before it was discovered. That is not how most major discoveries in physics work. In 1998, two independent teams studying type Ia supernovae, stellar explosions whose intrinsic brightness is well understood enough to use as distance markers, found that distant supernovae were fainter than expected. Fainter means farther. Farther, in an older universe, means the universe isn't just expanding. It's expanding faster than it should be, given the amount of matter present to slow it down. The universe's expansion is accelerating. Whatever is driving that acceleration has been named dark energy. It makes up roughly 68% of the total energy content of the universe. It does not cluster the way matter does. It fills space uniformly, exerting something like negative pressure, a tendency that drives expansion rather than opposing it. As the universe expands and dark energy's influence grows relative to the diluting matter, the expansion rate increases. Distant galaxies recede faster. The cosmological event horizon, the boundary beyond which nothing can ever reach us, moves closer in comoving coordinates. Galaxies that are today outside the event horizon, but inside the observable universe, will eventually cross further beyond reach. In roughly 2 trillion years, all the galaxies we can currently see, every galaxy outside our local group, will have receded past the event horizon. The sky will be dark. The observable universe, from the perspective of any civilization that exists in the remnant Milky Way, will contain only the merged stars of its own galaxy and a handful of gravitationally bound neighbors. Everything else will be gone, not destroyed, not dead, just gone from reach, moved beyond a boundary that, without dark energy, would never have existed in its current accelerating form. Space itself may be finite and still have no edge. Think about the surface of a sphere. You can walk in any direction on the surface of a sphere and never reach an edge. The surface curves gently, and eventually, if you walk long enough, you return to where you started. The surface has a definite area. It is not infinite, but it has no boundary, no edge. The question, what's beyond the edge, doesn't apply. The surface wraps back on itself. Now remove the sphere, but keep the surface. Try to think of it as its own space, not as a shell wrapped around something, but as a two-dimensional universe, curved and closed, with a definite size, but no outside and no boundary. That's a two-sphere. And the three-dimensional analog, a three-sphere or hypersphere, is one possibility for the shape of our universe. If our universe has that topology, traveling in any direction long enough would eventually bring you back to your starting point. The universe would have a definite volume, a definite size, not infinite, but no edge, no boundary, no outside to point to. Another option, a three-torus, like the surface of a donut extended to 3 dimensions, a space where traveling far enough in any direction brings you in from the opposite side. Finite volume, no edge, no center, no outside. These are not merely speculative, they are mathematically consistent geometries for a three-dimensional universe, studied seriously as alternatives to an infinite flat space. CMB measurements tell us the universe is very close to flat, ruling out a small hypersphere, but not ruling out a very large one, or an infinite flat space, or other geometries. The curvature, if it exists, is too gentle for current instruments to detect. The shape of the universe is genuinely unknown, and in some of these shapes, the question, what exists beyond the universe, has a surprising answer. There is no beyond, only around. Inflation's fingerprint is stamped on everything we can see. Begin with the quantum vacuum. At the Planck scale, the smallest meaningful length in physics, smaller than an atom by roughly 20 orders of magnitude. Space is not smooth. It seethes with quantum fluctuations, pairs of particles and antiparticles that wink into existence and annihilate almost instantly, energy that borrows against future repayment, ripples in the fabric of fields that exist even in what we call empty space. In ordinary conditions, these fluctuations are vanishingly small and have no effect on anything large. They are local, transient, self-canceling. But during inflation, they were not self-canceling. As the universe expanded at an exponential rate, tiny quantum fluctuations were stretched, literally, physically stretched by the expansion of space, from subatomic scales to macroscopic scales. What had been a quantum ripple smaller than a proton was amplified into a density variation the size of a galaxy cluster. Then, inflation ended. The universe cooled, and those density variations became the seeds of structure. The places where matter was slightly more concentrated, where gravity would slowly win, where gas would collapse into stars, stars into galaxies, galaxies into clusters. The cosmic web, every filament, every void, every supercluster in the observable universe, traces back to quantum fluctuations during inflation, in the first fractions of a second of time. The fluctuations that became the Milky Way. The fluctuations that became the Virgo supercluster. the fluctuations that became every structure we have observed or will ever observe in our entire history as a species. All of it, quantum static, stretched to cosmic scale. And the same process operated in regions beyond our observable universe. The same quantum fluctuations seeded the same structures there. Whatever exists beyond our horizon almost certainly has the same pattern, a cosmic web of filaments and voids, organized by the same physics, produced by the same primordial noise. The universe we cannot see is almost certainly recognizable to us in its structure. We just cannot see it. Beyond our horizon, stars are being born right now. Somewhere beyond the cosmological horizon, in this moment while you breathe, a molecular cloud of hydrogen and helium is collapsing under its own gravity. It has been gathering for millions of years, slowly concentrating, cooling, fragmenting. The fragments fall inward. The centers of those fragments heat up. Pressure builds until nuclear fusion ignites. A star is born. We will never know about it. We cannot detect it. Its light cannot reach us. Its gravitational influence is too distant and diluted to measure. If that star, billions of years from now, explodes in a supernova and scatters heavy elements into surrounding space, and from those elements a planet forms, and on that planet something eventually looks up, we will never know. No signal can cross the horizon. But it's happening. Right now. On the other side of a boundary drawn not in space but in the physics of light and time. The universe does not stop producing structure because it passes our horizon. The processes that built everything we can see, gravity, nuclear physics, the slow accumulation of matter, continue beyond what we observe. They do not require our observation to proceed. They have been proceeding for the entire history of the cosmos in regions we have never seen and never will. This is one of the stranger implications of modern cosmology. Most of the universe is not just unobserved, it is unobservable in principle forever. The action happening out there, star formation, galaxy evolution, the slow gravitational dance of clusters, all of it proceeds without us, without any possible witness from our corner of space. The universe is doing most of its work in private. And somewhere in that private vastness, as your breath slows and the room quiets, hydrogen clouds are falling inward, fusion is igniting. Light is being born that will never reach any eye we know of. The eternal inflation hypothesis makes the observable universe a local accident. The model is called eternal inflation, and its implications are disturbing in the best way. In standard inflationary cosmology, inflation ended. The period of exponential expansion came to a halt when the inflaton field, the field responsible for driving inflation, decayed into ordinary matter and radiation. That transition is called reheating, and it produced the hot, dense, matter-filled universe we inhabit. But in several variants of the theory, inflation doesn't end everywhere at once. It ends locally, in patches, while continuing in surrounding regions. The regions where inflation ends become bubble universes, isolated regions of space where the inflaton field has decayed and ordinary physics applies. Each bubble expands internally, following its own Big Bang. But outside those bubbles, inflation continues, producing more bubbles, and more, and more. In this picture, inflation is eternal. It has been producing bubble universes continuously, perhaps since before our own bubble formed. It will continue producing them indefinitely, in regions of space expanding faster than the bubbles can catch up with each other. Each bubble universe is, in this model, causally isolated from the others. The space between bubbles is expanding so fast that no signal can cross from one bubble to another. Each universe, including ours, is effectively alone. This model has testable predictions. If our bubble formed from eternal inflation, it may have collided with other bubbles in the distant past, leaving imprints in the CMB, circular patterns of unusual temperature. Astronomers have searched. The results are ambiguous. No confirmed detection, no ruled-out detection. The observable universe in the eternal inflation picture is a single island in an archipelago spread through an inflating background. Most of those islands we will never see. Most of them may not know we exist. We may be one of countless local universes, each alone in its own ocean. A universe with different constants would be unrecognizable. If you change the strength of the electromagnetic force by even a small fraction, hydrogen cannot form. Or if it forms, it cannot combine into heavier elements in stellar cores. Or if it can, the stars burn out too quickly for planets to form complex chemistry. Or the protons that form atomic nuclei fly apart before they can bind. The universe we inhabit is extraordinarily sensitive to the values of its fundamental constants. The fine structure constant, which governs electromagnetic interactions, must fall within a narrow range for atoms to be stable. The cosmological constant, which determines the expansion rate, must be nearly zero, but not exactly zero, for structures like galaxies to form. Too large, and the universe expands so fast that matter never clumps. Too small, and gravity wins everywhere, and the universe collapses. One interpretation of this sensitivity: there are many universes, each with different values for the constants, and we live in one of the rare ones where the parameters permit the kind of complexity that produces observers. We don't see the universes with incompatible constants because no observers exist there to look. This is the anthropic principle. It is philosophically unsatisfying to many physicists because it explains our situation by invoking an ensemble of universes we cannot observe. It is a selection effect, not a prediction. If the multiverse interpretation is correct, then regions beyond our horizon, other bubble universes in the eternal inflation picture, may have different values for the fundamental constants, a different electromagnetic force, a different cosmological constant, different particle masses. In those universes, atoms may not form as we know them. Chemistry may not emerge. In some, the universe collapses almost immediately. In others, it expands so rapidly that matter never congregates into anything. We do not know if those universes exist. We cannot see them. And even if we found evidence for their existence, we could never visit or communicate with them. The fine-tuning that makes our universe recognizable to us is, in those other regions, simply absent. They are not far away. They are incompatible, operating under physics that has nothing in common with ours. The Rhionization era burned through the universe's first dark age. Between about 380,000 years after the Big Bang, when the CMB was released, and roughly a billion years afterward, the universe was dark. The fog that had filled the early universe cleared at recombination, but what replaced it was not illuminated space. It was neutral hydrogen gas, stretching uniformly across the cosmos, absorbing most of the ultraviolet light that would subsequently be produced. The universe was dark not because nothing existed, but because the matter that existed was not yet organized into stars, and the neutral hydrogen absorbed what little light was available. This period is called the Cosmic Dark Age. Then the first stars formed. The first stars were not like the Sun. They formed from pure hydrogen and helium, no carbon, no oxygen, no iron. Without those heavier elements to cool the collapsing clouds efficiently, the first stars formed in massive, hot, short-lived configurations. Some were hundreds of times more massive than the Sun. They burned intensely and briefly, perhaps only a few million years, before exploding in supernovae that scattered heavy elements into the surrounding medium. But before they died, they radiated. They flooded the surrounding hydrogen with high-energy ultraviolet photons. Those photons stripped electrons from hydrogen atoms, ionizing the gas, converting it from neutral hydrogen back into a plasma state. Bubbles of ionized hydrogen formed around early sources of radiation, grew, and eventually merged. Over several 100 million years, the neutral hydrogen of the cosmic dark ages was burned away. By about a billion years after the Big Bang, the universe was largely transparent again. The universe lit up. This process happened beyond our direct view. The James Webb Space Telescope is now detecting some of the earliest galaxies, pushing observations closer to that transition. But the Rhionization era itself is something we reconstruct more from theory and inference than from direct observation. And beyond our horizon, the same dark age occurred, the same first stars, the same burning away of the fog, the same lighting of a previously dark sky, witnessed by no one, in a region of space we will never see. The Boltzmann brain problem is a crack in the foundation. Ludwig Boltzmann was one of the greatest physicists of the 19th century. He developed the statistical foundations of thermodynamics, understood entropy more deeply than almost anyone of his era, and he was tormented by a problem he couldn't fully resolve. The laws of thermodynamics apply statistically. In a sufficiently large system, over a sufficiently long time, random fluctuations will produce virtually any configuration, including highly ordered configurations that should normally be considered wildly improbable. Given enough time and space, a random fluctuation could assemble a fully formed brain, complete with memories, sensory apparatus, and the subjective experience of existing from the surrounding thermal noise. This is called a Boltzmann brain. It is a real prediction of statistical thermodynamics in a universe with infinite time or infinite space. Here is the disturbing part. If Boltzmann brains arise spontaneously from thermal fluctuations, they should vastly outnumber observers who arise through ordinary processes. Biological evolution on planets orbiting stars in well-formed galaxies. The universe we observe, with its vast structure and long causal history, is far more ordered than what a typical fluctuation would produce. A fluctuation that produced a single brain with false memories of a structured universe would be far more probable than a fluctuation that produced the entire observable cosmos. If Boltzmann brains outnumber ordinary observers, then statistical reasoning suggests that we are almost certainly Boltzmann brains, experiencing a hallucination of a structured universe, rather than the products of 4 billion years of biological evolution on a real planet. This is not a problem with a clean resolution. It emerges naturally in any cosmological model that involves very large or infinite time, including eternal inflation, including the long thermal future of an expanding universe. The problem has been known for decades, and physicists haven't solved it. Some cosmological models are ruled out partly by whether they predict Boltzmann brain problems. Others are considered more promising partly because they produce a universe finite enough that ordinary observers outnumber random ones. Beyond our horizon, if the universe extends far enough, the production of Boltzmann brains may be inevitable. They may already be forming, in the vastness of distant regions, in the thermal noise of an old and cooling cosmos. We cannot observe this. We cannot rule it out. The string theory landscape predicts more universes than any number names. String theory, as a mathematical framework, has an unusual property. It contains an enormous number of consistent solutions. When physicists work out the mathematics, a framework that attempts to unify all fundamental forces by describing particles as tiny vibrating strings, they find the theory doesn't specify a unique vacuum state. A vacuum state is the lowest energy configuration of a system, and in quantum field theory, different vacuum states correspond to different values for the fundamental constants, different cosmological constants, different particle masses, different strengths of forces. String theory's landscape, the collection of all consistent solutions, is thought to contain on the order of 10 to the 500th power distinct vacuum states, a number with 500 zeros. No quantity in physics has ever reached this scale. Each vacuum state in the eternal inflation picture corresponds to a different possible bubble universe. As inflation produces bubbles, each bubble forming when the inflaton field decays to a particular vacuum state, it samples from this landscape. Different bubbles correspond to different solutions, different physical constants, different particle masses. Our universe corresponds to one vacuum state in the landscape, one particular collection of constants that permits atoms, chemistry, stars, and galaxies. Other vacua may not permit any of these. The landscape was initially viewed as an embarrassment, evidence that string theory was underdetermined and couldn't make specific predictions. If the theory allows 10 to the 500th power solutions, it predicts everything, which effectively means it predicts nothing. The anthropic interpretation transformed this. If there are that many universes sampling the landscape, it's unsurprising that at least some have constants compatible with observers. and we necessarily find ourselves in one of those. The mathematical framework is consistent. The physical implications are staggering. And none of it can be tested directly, because the other universes in the landscape are precisely those that are beyond any possible observation. The farthest object we have ever detected was already moving away when its light left. In 2023, astronomers using the James Webb Space Telescope confirmed the detection of a galaxy, designated JD's GS Z14-0, at a redshift of approximately 14.3. That places it at a time when the universe was only about 290 million years old, roughly 2% of its current age. The light we received from that galaxy left when the universe was less than 300 million years old. At that moment, the galaxy was located approximately 2.8 billion light-years from what would eventually become the Milky Way. Not far, in cosmic terms, but space was expanding and the galaxy was moving with it. By the time its light reached us, the galaxy itself had moved to a distance of more than 33 billion light-years. It is now so far away that even if it sent us a signal this moment, traveling at the speed of light, that signal would never reach us. The expansion of space between us and that galaxy exceeds the speed at which light can cross it. What we received was a message written 300 million years into cosmic history, sent across space, transformed by billions of years of travel and expansion into a faint smear of light that Webb's instruments deciphered into a redshift, a luminosity, a rough mass estimate. The galaxy itself, whatever it has become in the intervening 14 billion years, is beyond reach. Its first stars have long since died. Subsequent stellar generations have formed, burned, exploded. It has possibly merged with other galaxies. Its current form is unknown to us and will remain so. We received a 14 billion-year-old signal from something that is now permanently beyond our event horizon. And that is the closest thing we have to looking beyond the observable universe. The photons that arrived at Webb were carrying the faintest echo of the earliest structures in cosmic history. They traveled the entire age of the universe to reach a mirror in space, 1.5 million kilometers from Earth. They were absorbed by a detector the size of a dining table. Your own photons, the infrared warmth radiating from your skin right now, are doing the same thing. Moving outward, crossing distances no signal will retrace, carrying the information of this moment into a universe that will not preserve it. Gravity may reach beyond, where light cannot. Here is a question that has not been cleanly answered. The observable universe has a boundary, the cosmological horizon, beyond which light cannot reach us. Light is the carrier of most of our information about the cosmos. No photons from beyond the horizon, no direct information. But gravity is different. Gravity is not carried by photons. In the framework of general relativity, it is a curvature of spacetime. The presence of mass creates a geometry that other masses respond to, and gravitational fields don't propagate from an object like a signal in the same way. They are a feature of the spacetime surrounding the object. More precisely, the gravitational field of a distant object is present in your local spacetime because it was present in your past light cone, the region of spacetime that is, in principle, causally connected to you. Objects that were once within our horizon may have moved beyond it, but the gravitational field they established when they were within range is still here. This opens a theoretical possibility. Structures beyond the current cosmological horizon, including structures in the very early universe that are now out of reach, may have left gravitational imprints in the structure of space-time that we could, in principle, detect, not by seeing those objects, but by reading their gravitational influence in the distribution of matter we can observe. Whether this is the explanation for the anomalous bulk flows in the local universe, the motion of galaxies that doesn't fully fit simple models, is not settled. It is a hypothesis, not a conclusion. But the possibility that something beyond our sight is gravitationally influencing what we can see, that the invisible is shaping the visible, is permitted by the physics. We don't know if it's true. We don't know how we would distinguish it from gravitational effects produced entirely by structures within our observable universe. Tonight, this is where the science stops, not because the question is unimportant, because we genuinely don't have the answer. An infinite universe contains every pattern that can exist. Start with a game. Take a coin, flip it, heads or tails. Now flip it again, 1 billion times, 2 billion, keep going. In the sequence of 1 billion flips, almost certainly, there will be a stretch of 10 heads in a row, of 50 heads in a row, of 1 million heads in a row if you flip long enough. Every pattern that can occur in a finite sequence will eventually occur, given enough trials. Not because the coin is special, because the space of possibilities is finite and the number of trials is large enough. Now apply this to the universe. If space is infinite, if the universe truly extends without end, then the number of possible arrangements of matter in any finite region is also finite. The number of ways you can arrange atoms in a cubic light-year of space is enormous, but bounded by the laws of physics, by the number of particles, by the possible states of each. In an infinite universe, if matter is distributed more or less uniformly, which observations suggest it is, on the largest scales we can observe, then every possible arrangement of matter in a finite region will eventually be realized somewhere. Every configuration, including this one, including you in this room, with these thoughts, in exactly this physical state. Not a version of you, exactly you. In an infinite universe, this configuration of matter, you, here, now, exists infinitely many times in regions so distant that no signal has ever passed between them. The nearest copy of this exact configuration would be approximately 10 to the 10 to the 29th meters away. A number that cannot be written out in a universe-sized book. But the logic is straightforward. In infinite space with finite configurations, repetition is not just possible, it is inevitable. This follows from standard cosmology applied to an infinite universe. The observable universe's finitude is a local limit of our sight. If the underlying space is infinite, every possible pattern is somewhere, What that means for identity, for experience, for the uniqueness of a single life, that's a question physics cannot and does not address. Only the fact, in infinite space, every possible pattern is somewhere. The cosmic web extends beyond our sight in every direction. When astronomers map the positions of hundreds of thousands of galaxies in three-dimensional space, they find not a random scatter, but a network. Filaments of galaxies stretching for hundreds of millions of light-years, connected at nodes where clusters accumulate, with vast, empty regions, cosmic voids, occupying the spaces between. The whole structure looks like a foam or a web, or the inside of a sponge. It's called the cosmic web, and it fills the entire observable universe. But the cosmic web does not stop at our horizon. The physics that built it, the primordial density fluctuations seeded by inflation, the slow gravitational collapse of dark matter into filaments, the sliding of ordinary matter along those filaments into clusters. Those processes operated across the entire universe, not just the part we can see. There is no reason for the web to terminate at our horizon. The horizon is a limit of our observation, not a feature of the cosmos. Beyond our sight, the filaments continue, the voids continue. Clusters of galaxies accumulate at nodes that no telescope will ever reach. Walls of galaxies stretch across vast regions of space that have never reflected light toward any observer we know of. The observable universe is a finite window into a web that is almost certainly much, much larger. Whatever structures exist beyond our horizon, superstructures, great walls, voids spanning billions of light-years, they are inaccessible. They will never appear in any survey. We have mapped roughly 1,000th of the observable universe in 3 dimensions with good precision. The observable universe represents perhaps 1/1000th of the total in the more conservative estimates. The cosmic web we've mapped is a tiny sample of a structure we will never fully see. And still, it is enough to recognize the pattern, enough to say with confidence, it continues, everywhere, in every direction. In the dark beyond the dark. The topology of space may mean you cannot go beyond, only around. Imagine walking in a straight line forever and arriving back where you started. Not because you curved your path, not because you walked in a circle, in a perfectly straight line for an incomprehensible distance, and you returned to your starting point. This is what would happen if the universe has the topology of a 3 torus. In a 3 torus, space is periodic. Traveling far enough in one direction brings you back to your starting position, as if you'd passed through a wall and emerged from the opposite side. The same in every direction. The universe wraps. It has no edge, no center, no boundary. It is, in every direction, self-returning. The implications are strange. If the universe is a 3 torus small enough that light has had time to travel around it, we would see multiple images of the same galaxies in different directions. We would see our own galaxy, from behind, as it appeared billions of years ago. Ghost images, the same structures appearing in different parts of the sky, the same patterns recurring. We've looked for this. We haven't found it. That doesn't rule it out. It only constrains the minimum size. If the torus is larger than the observable universe, the ghost images are beyond our horizon. We would have no way to detect the periodicity from inside. A 3-torus universe has no beyond. Beyond is just the same universe, wrapped. The question, what exists beyond the observable universe in a toroidal cosmos, has an answer: more of this. Eventually, traveling far enough in any direction, you'd circle back to here. That possibility hasn't been ruled out by any current observation. The universe might be periodic. Space might fold. What we call the far edge of sight might be, in a closed topology, a direction that points, in a vast, slow loop, back home. The first light of Ryanization was invisible to every eye that existed. A single hydrogen atom, proton in the center, electron in orbit. Electrically neutral, invisible to most forms of radiation, one of the roughly 10 to the 80 atoms in the observable universe. One of the dominant forms of ordinary matter in the early universe after recombination. The hydrogen atom absorbs ultraviolet photons very effectively at specific wavelengths, particularly at a wavelength called Lyman alpha, which corresponds to the energy required to move an electron from its lowest energy state to the next one up. When that photon is absorbed, the atom is excited. Moments later, it emits the photon again, but not necessarily in the same direction. The photon scatters. It propagates no further along its original path. This single mechanism, one atom absorbing one photon and redirecting it, is why the early universe was opaque to the light from the first stars. The neutral hydrogen that filled space after recombination scattered ultraviolet photons so effectively that early stellar light couldn't travel far. The first stars shone, but their light was trapped in the surrounding fog, absorbed and reabsorbed, scattered endlessly through clouds of neutral gas. Then the ultraviolet photons accumulated. As more stars formed, ionizing radiation increased. Bubbles of ionized hydrogen formed around the densest star-forming regions, regions where the gas had been stripped of electrons, made transparent. Those bubbles grew. They overlapped. They merged. Over several 100 million years, the entire intergalactic medium was ionized. The universe became transparent to the light of its own stars. That transition, the epoch of Ryanization, is one of the most dramatic phase changes in cosmic history. It is the moment the universe went from being a fog to a clear medium. No observer witnessed it. No eyes existed anywhere in the cosmos at that moment to see the fog clear. The light released when the Ryanization completed has been traveling for nearly 13 billion years, and it is only now, in this era, reaching instruments that humans have built. A single hydrogen atom, absorbing a single photon, repeated across every atom in the observable universe, across hundreds of millions of years. That was the mechanism by which the universe illuminated itself. And beyond our horizon, the same fog burned away in the same way, witnessed by no one, releasing light that will never reach us. Poincaré recurrence implies the universe will eventually repeat. Henri Poincaré demonstrated in the late 19th century that a closed mechanical system will eventually return arbitrarily close to any earlier configuration, given enough time. This is the Poincaré recurrence theorem. The time scale involved is staggering. For a system the size of the observable universe, the Poincaré recurrence time would be a number so large that the total age of the universe, 13.8 billion years, is less than a single decimal place in its representation. The number would require more digits to write than there are atoms in the observable universe. For a universe with dark energy, the situation is more complicated. Dark energy drives expansion, continuously increasing the accessible volume and, in the long term, diluting matter and energy toward maximum entropy. Whether Poincaré recurrence applies to a universe undergoing eternal expansion is debated. Some physicists argue it doesn't, because the system isn't truly closed. But in the early 2000s, this discussion contributed to the Boltzmann brain problem and related puzzles about the statistical validity of our universe's current ordered state. If the universe is old enough and quantum fluctuations can generate any state, then the random assembly of a structured universe like ours requires explanation. A simpler fluctuation, producing less order, would be far more probable. The recurrence time, to the extent it applies, is on the order of 10 to the 10 to the 122nd power years, a number that has no physical meaning in any familiar framework. A number so large it contains every possible state of the observable universe, sequentially, with time left over. In that kind of time, the universe we observe might assemble again, not through any mechanism that resembles our Big Bang, through pure statistical recurrence. We don't live anywhere near that timescale. We're in the first few seconds of the first frame of the first scene of a story that will run for an incomprehensible duration. The void between galaxy filaments is not empty. When astronomers first mapped the large-scale structure and found cosmic voids, vast regions spanning hundreds of millions of light-years with very few galaxies, the temptation was to call them empty. They're not. Cosmic voids contain dark matter. They contain tenuous wisps of hydrogen gas left over from the early universe's diffuse intergalactic medium. They contain photons, light passing through in every direction. They contain the cosmic microwave background, present uniformly everywhere, carrying the temperature of the universe's ancient transition. They contain neutrinos, produced in vast quantities in the early universe and now streaming through everything, almost unimpeded. They contain, probably, occasional rogue planets ejected from stellar systems, drifting without a sun. What voids don't contain is the concentration of matter that makes galaxies, stars, chemistry, and the kinds of structure we recognize. But absence of concentration is not absence of substance. The voids between filaments occupy most of the volume of the universe. Roughly 80% by volume, in some estimates, is void. The galaxies, the clusters, the filaments. These are the thin threads of a net. The void is the water the net sits in. And beyond our horizon, those voids continue. In the regions we cannot observe, the cosmic web's filaments thread through vast empty spaces just as they do here. The voids there are as real as the ones here, as full of dark matter and photons and silence, just completely beyond our reach. The universe is mostly void. What we can see is the minority. What exists beyond our sight is mostly the same kind of nothing, which is to say, something. Light reaching us, now left before the Earth had any oceans. The most distant galaxy confirmed before the Webb era sent us light when the universe was about 400 million years old, roughly 3% of its current age. The light we received from it had been traveling for approximately 13 billion years. During that time, the solar system formed from a molecular cloud that hadn't yet begun to collapse. The Earth solidified from a debris disk. The Moon was blasted loose by a collision that reshaped the early Earth's geology. Oceans formed from water delivered by comets and asteroids. The first microscopic life appeared, perhaps 3.5 billion years ago. Photosynthesis transformed the atmosphere. Animals evolved. Dinosaurs appeared, thrived for 160 million years, and were extinguished. Mammals spread across the continents. Our species emerged less than 300,000 years ago. All of that happened while the light was traveling. It left a galaxy still forming its first stars, in a universe still emerging from its dark age. It moved through expanding space for 13 billion years, redshifting as it traveled, stretching from ultraviolet into infrared, arriving at a mirror in space where it was detected and analyzed. We looked at photons that are 13 billion years old and extracted from them a galaxy's luminosity, its mass, its likely stellar population. The light you perceive right now, from a lamp, from a screen, reflected from the ceiling, is ancient by human standards, but almost instantaneous by cosmic ones. The oldest light we can detect is separated from you by an incomprehensible span of time. And beyond the reach of even the oldest light, more universe, more time, more space that we can never observe, filled with things we cannot name. Something may exist before the Big Bang, and we cannot tell. The Big Bang, as a concept, is often misunderstood. It is not the moment of creation. It is the earliest moment described by our current physical models, the point beyond which the standard equations of general relativity break down, returning infinite densities and temperatures that physics cannot handle. The Big Bang singularity is not an event we've observed. It is a feature of the equations, a placeholder marking the edge of applicability of our best theory. What actually happened at that instant, or before it, requires a theory of quantum gravity that we don't yet have. Several models attempt to describe a pre-Big Bang state. In loop quantum cosmology, the singularity is replaced by a bounce, a prior era of contraction that reached maximum density and then rebounded into the expansion we call the Big Bang. The universe did not begin. It cycled. Before our universe expanded, there was a contracting universe. The physics of the bounce connects the two. In string gas cosmology, the universe emerged from a phase where all dimensions of space were small and compact, tangled in high-energy configurations. The Big Bang represents the moment 3 spatial dimensions expanded while the others remained compact. In conformal cyclic cosmology, proposed by Roger Penrose, the universe undergoes an infinite sequence of aeons, each beginning with a Big Bang and ending with a vast, cold, structureless future. The end of one aeon is mathematically similar to the beginning of the next, creating a cyclic pattern with no overall start. These models are speculative. They make some predictions, but those predictions are at the edge of what current instruments can test. Penrose has claimed to detect signals in the CMB that he interprets as evidence of aeons before ours. Other researchers disagree with his analysis. The state of the question is, we do not know if anything came before the Big Bang. Our physics stops at that boundary. We do not know if before is even a meaningful concept when applied to the origin of time itself. Tonight, this is where it ends, not with resolution, with the honest edge of knowledge. The observable universe is only our neighborhood. The Milky Way is roughly 100,000 light-years across. That feels large. In the local group, the cluster of galaxies gravitationally bound to our own, there are roughly 80 galaxies, most of them small. The diameter of the local group is about 10 million light-years, larger. The Virgo supercluster, of which the local group is a peripheral member, spans roughly 110 million light-years, larger still. The Virgo supercluster is itself a lobe of an even larger structure, the Laniakea supercluster, identified in 2014 by Brent Tully and collaborators by mapping velocity flows of galaxies. Laniakea spans roughly 500 million light-years and contains the mass of roughly 100 million billion suns, distributed across 100,000 galaxies. Laniakea is one structure among many. The Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, the largest known structure in the universe, stretching roughly 10 billion light-years, though its status as a single coherent structure is debated. The observable universe, 93 billion light-years across, contains all of these. It seems enormous. It is the largest scale we have direct observational access to. But the observable universe is one patch in a total universe almost certainly hundreds to millions of times larger. Whatever structures exist beyond our horizon, superstructures, great walls, voids spanning billions of light-years, they are inaccessible. They will never appear in any survey. They will never register on any instrument. The Milky Way is our neighborhood. The local group is our district. Laniakea is our city. The observable universe is our continent. And the total universe is a world whose shores we have never seen and cannot reach. The fate of the observable universe is already written. If current cosmological models are correct, and they have been tested against observations to high precision, the observable universe's long-term future follows from the nature of dark energy. Dark energy, if it remains constant, which is the simplest model consistent with current data, will drive the expansion of the universe to continue accelerating indefinitely. Galaxies beyond our local group will gradually recede beyond the event horizon. The universe accessible to any descendants we might have will shrink, not in size, but in content. Fewer and fewer galaxies will be observable. The sky will grow darker. On a timescale of roughly 100 billion years, roughly 7 times the current age of the universe, all but a few dozen galaxies will have receded past the event horizon. The sky will be populated by the merged remnant of the Milky Way and Andromeda, a collision expected in about 4 billion years, surrounded by darkness. On a timescale of roughly 10 to the 14th years, stars will stop forming as gas reservoirs are exhausted. Existing stars will burn out. The universe will be populated by white dwarfs, neutron stars, and black holes. On longer timescales, trillions upon trillions of years, even these remnants will change. White dwarfs will slowly cool to black dwarfs. If protons decay, a process not yet confirmed but predicted by some extensions of the Standard Model, ordinary matter will gradually dissolve. Black holes will eventually evaporate via Hawking radiation over timescales so long that the current age of the universe is negligible by comparison. What remains after all of this is a cold, sparse, nearly structureless universe in a state of maximum entropy, dark and vast and still. And beyond our current horizon, the same fate unfolds. Whatever structure exists, there will have burned out in the same way. The cosmic web will have unraveled. The voids will have grown more void. Everything equalized by time. The multiverse is not science fiction. It is what several mainstream theories predict. The word multiverse sounds invented. In popular imagination, it suggests infinite parallel worlds where every possible choice has been made, every history played out. The scientific usage is more specific and, in some ways, stranger. There are at least 4 distinct ways that modern physics predicts the existence of other universes. The cosmologist Max Tegmark organized them into levels. Level 1. The simplest. If the universe is truly infinite in spatial extent, then every possible arrangement of matter that can occur will occur somewhere, infinitely many times. No drama required, just standard physics applied to infinite space. Level 2. The eternal inflation multiverse. If inflation is eternal and produces bubble universes with different values of the physical constants, then other regions of the inflating background have physics different from ours. These regions are causally disconnected from us. We cannot observe them. Level 3. The quantum many-worlds interpretation. In the Everett formulation of quantum mechanics, every quantum event results in a branching of the wave function. Every possible outcome occurs in a separate branch. The branches don't communicate. All are equally real within the mathematical framework. Level 4. The mathematical universe hypothesis. If every mathematically consistent structure exists as a physical reality somewhere, then every possible physics, not just different constants, but entirely different laws, is realized. None of these is fringe science. Level 1 follows from cosmological observations and simple geometry. Level 2 is the natural extension of inflation, the most widely accepted model of the early universe. Level 3 is a preferred interpretation of quantum mechanics among a significant fraction of physicists. Level 4 is more speculative, but a logical extension of the same principles. We cannot observe any of these other universes. That is precisely what makes them other universes rather than parts of ours. But their existence is not fantasy. It's a prediction or a consequence of the best physics we have. What we call the universe may be the smallest possible unit of what actually exists. A civilization beyond our horizon would consider us mythological. Consider what it would mean to be an observer in a galaxy beyond our cosmological horizon. Assume physics works there the same way it does here. The same fundamental constants, the same laws, the same speed of light. Assume that civilization has developed technology comparable to ours, or more advanced. They observe the universe around them. They map the CMB. They study large-scale structure. What would they see? Their own cosmic web, their own local group, their own version of the history of structure formation. They would see the CMB originating from all directions, representing the moment of recombination in their region of space. But they would not see us. The Milky Way lies beyond their cosmological horizon. Light from our galaxy cannot reach them, not because of any failure of physics, because the universe is too large and has been expanding for too long. We are, from their perspective, as permanently invisible as the regions beyond our horizon are to us. More than invisible, we are outside their observable universe. We do not exist in their observable cosmos at all, not as a faint smudge at the edge of detection, not as a theoretical object their instruments are close to resolving. We simply do not appear in their sky in any form. To that civilization, we are less than myth. Myth requires some trace of a thing to distort into story. We leave no trace in their observable universe. We are a configuration of matter in a region their physics has no access to, ever. And they are the same to us. The asymmetry is complete. Each local universe is sealed. Each observer is embedded in their own horizon, looking outward, seeing their own history, constructing their own picture of a cosmos they can only partially read. We are all alone in exactly the same way. The first second of time produced everything that would ever exist. Not the first minute, not the first hour, the first second. In the first second after the Big Bang, the universe passed through a series of phase transitions that established the fundamental content of the cosmos. By the time 1 second had elapsed, the ratio of protons to neutrons that would eventually determine the ratio of hydrogen to helium in every star and galaxy that would ever exist was already fixed. In the first fraction of a second, the universe was a quark-gluon plasma, so hot and dense that the particles we normally think of as fundamental hadn't yet assembled from their constituent quarks. As the universe cooled through the first microsecond, quarks combined into protons and neutrons. As it cooled further through the first few minutes, protons and neutrons combined into the nuclei of the lightest elements, helium, deuterium, tiny traces of lithium. By the time 3 minutes had passed, Big Bang nucleosynthesis was complete. The elemental composition of the universe, roughly 3/4 hydrogen and 1/4 helium by mass, was set. Almost all the hydrogen and helium in every star in every galaxy in the observable universe and in every galaxy beyond our horizon traces back to those 3 minutes. The rest, carbon, oxygen, iron, all the heavier elements, was built later, in stars. But the raw material was established in the first 3 minutes of time. In the first second, before any star had formed, before any galaxy had assembled, the universe established the foundational ratios that would govern the chemistry of everything that would ever exist within it. What you're made of was decided in the first second. What exists beyond our horizon was made from the same primordial inventory. Dark matter structures. Everything we cannot directly see. There is a component of the universe that neither emits light nor reflects it. It does not absorb photons. It does not interact with ordinary matter through any force we have detected except gravity. It passes through planets, stars, and the human body without leaving a trace. We have never directly detected a dark matter particle. Every experiment designed to catch one has returned empty results. Deep underground detectors shielded from cosmic rays, particle collider searches for gamma-ray signals from dark matter annihilation in galactic centers, nothing confirmed. And yet dark matter is not speculative. It is the best supported invisible thing in science. Its gravitational effects are everywhere. Without it, galaxies spin at rates that would fling their outer stars into intergalactic space. The stars on the outer edges of galaxies move too fast for the visible matter to hold them. Without it, the CMB would look different. Without it, the cosmic web could not have formed in the time available. Ordinary matter alone is too weakly interacting to have collapsed into the structures we observe in the universe's history. Dark matter seeded the cosmic web before ordinary matter did. It clumped first, under gravity, forming the scaffolding into which ordinary matter later fell. Every galaxy we observe is embedded in a dark matter halo vastly larger than its visible disk. The Milky Way's dark matter halo extends for perhaps 300,000 light-years in every direction, 3 times the diameter of the galaxy's visible stars. Beyond our horizon, this continues. Dark matter extends through the cosmic web in regions we cannot observe. It is the skeleton of a universe that is mostly invisible to us, in a vast region of space that is invisible to us, structured in ways we understand from physics but can never verify directly. We live inside a structure made mostly of something we have never touched, and beyond what we can see, more of that same invisible architecture extends, doing its slow gravitational work in the dark. The universe may have no beginning in any direction. One of the stranger proposals in modern cosmology is the idea that the universe might be self-contained, not created from something, but simply existing without a moment before which nothing was. Not nothing in the everyday sense, nothing in the strict sense, no space, no time, no matter, no energy, no laws. A technically careful version of this idea comes from the Hartle-Hawking no-boundary proposal. In quantum cosmology, Hawking and James Hartle proposed that the universe might be described by a quantum state with no boundary in imaginary time, a description in which the beginning of the universe is analogous to the south pole of a sphere. At the South Pole, there's no before. It's not that something happened before the South Pole. The South Pole simply is where the sphere ends. Asking what came before the Big Bang in this model is like asking what is south of the South Pole. The universe, in this picture, is self-contained. It has no boundary in time, no creator required by the mathematics. The laws of physics are the only ingredient. This is not a physical proof. It is a mathematical proposal. Whether it accurately describes reality is unknown. Whether it can be tested at all is an open question. But the question it addresses, what started everything, is one that physics has approached more seriously than it's given credit for. The answer isn't simple. It might be that the question doesn't have the shape we think it has. The universe might not have needed a beginning any more than the surface of a sphere needs a southernmost starting point. The universe beyond our horizon in this picture was not caused by something. It simply is, as we are. That might be the hardest thing physics has ever asked us to accept. Not that the universe is vast, not that we are small, but that there may be no story of how it began. Only the fact that it is in all directions, everywhere, without exception. The universe we cannot see outnumbers the one we can. Let's be clear about the proportion. If the universe is roughly 250 times wider than the observable universe, a conservative estimate from the flatness of the CMB, then the observable universe represents about 1 part in 15 million of the total volume. We can see less than a millionth of what exists. If the universe is 1,000 times wider, the ratio is 1 to a billion. If inflation produced the vast stretches that some models suggest, the ratio may be 1 to numbers that dwarf any estimate we can meaningfully express. In every direction, beyond what we can see, the cosmos continues. Galaxies are clustering into groups. Groups are assembling into clusters. Clusters are threading into filaments. Filaments are bounding voids. Voids are as large as what we see here. The whole architecture is the same, built from the same physics, the same dark matter, the same dark energy, the same fundamental constants. Whatever exists out there does not know about us. We cast no light in their direction that will ever arrive. We exert a gravitational pull so diluted by distance that no instrument could distinguish our contribution from background noise. We are completely unknown to whatever might be looking outward from beyond our horizon. And we don't know about them, can't see them, can't reach them, can't hear them. The universe is doing most of its existing outside the small sphere of space from which any signal has ever reached us. The stars that are burning right now, in galaxies beyond our horizon, are burning in complete privacy. The voids that are emptying further are doing so without witness. The structure assembling, slowly through gravity's patient work, is assembling in silence. We are here, in this room, in this moment, inside a bubble of received light that is the entirety of our cosmos. And the cosmos is enormous. And this room is warm, and you are breathing. And everything that exists is enormously, quietly, permanently at work, seen and unseen, here and far beyond here, continuing without pause in the dark. We've drifted through horizons that are not walls, through galaxies that number in the trillions and are themselves the minority, through dark matter that structures everything without touching anything, through the moment the universe first became transparent, through the sound that moved through plasma for 380,000 years before being frozen into the geometry of space, through the dark age and the burning away of the fog, through the quantum fluctuations stretched to the scale of superclusters, through bubble universes alone in inflating oceans, through the question of what came before the beginning and the honest answer, we don't know. What lies beyond the observable universe is, in the most literal sense, unknown to us. But it is almost certainly not empty, almost certainly not different in its fundamental architecture, and absolutely, permanently, irreversibly out of reach. That is not a tragedy. It is the nature of being somewhere in a universe that is everywhere. You are here. That is already an extraordinary position. You are a configuration of matter that can receive ancient light, carry the weight of a question too large for any single mind, and then, remarkably, set it down. If your eyes feel heavy, let them close. If this felt like your kind of place, leave a comment when you wake up. And if you're still here, the next chapter is waiting. Another edge, another horizon, another piece of the universe we carry together. The universe will still be here when you wake up. So will we. Good night.